Hello, I want to give a couple examples of Gaussian elimination. This is a little bit different than Gauss-Jordan elimination, which is often found on the internet. So for Gaussian elimination, you're getting your matrix into row echelon form. Versus Gauss-Jordan elimination, you're getting into reduced row echelon form. And I think the row echelon form it has, one extra step. I think that step's maybe easier than trying to get it into that reduced row echelon form for many of us. I'm only going to be discussing the systems of two equations in this video. So here are a couple examples. So row echelon form is where you have one's long diagonal, 0 below. Reduced row echelon form would be if you would also have a 0 here with everything above the diagonal. What this last line is basically telling you, just like we're going to write the matrix for this system, is 1x plus however many y's equals whatever this is, and 0x plus 1y equals whatever this is. And so this last line essentially tells you what your y value is, because it's 1y equals that number. And then you can substitute that in for the y of your first equation. So let's go ahead and write this system as a matrix. So we have a coefficient of 1 for the x, 3 for the y, vertical line for the equals, -1. This is an augmented matrix because you are putting in your constants. Coefficient of 4 for the x, -5 for the y, and 13 is your constant. So again, this first column are the x's, second column y's, the vertical line stands for the equal sign, and then your constant. So it's just a shorthand way of doing elimination method, but it's elimination of x's, because that's the x column, x's. And then solving for y, and then plugging in your y and solving for x. So it is essentially elimination, but in a shorthand version where you don't have your x's and y's, and you specifically are getting rid of the x first, even if the y's would have been easier. So our goal is to have a 1 in this position, and we have it. So we really lucked out. For the next step, we want to get a 0. So that means we are trying to get rid of the x's. So imagine this system, which it is, right? This system, we're trying to get rid of x's. What would we do? We would multiply the top one by -4 and add it to this bottom one. We would get a opposite coefficient for one of my variables, and in this case, specifically the x. So I'm going to go ahead and show that I'm multiplying by -4. And what I would get, this is just my scratch work, is -4, -12, and +4. For my next line, I have 4, -5, and 13. So we successfully got 0. We'd have -17 and +17. So sometimes people won't show this work. They just do it in their head, or they write down the rule that they're doing. In this case, -4 times row 1 plus your row 2 will be replacing your row 2 to make it closer to that format, the row echelon form. So your first equation is still a valid equation for this system. And the second one, we have basically multiplied and added to eliminate. Does that sound familiar from elimination method? We multiply one of our equations, we added, and we've eliminated our x. So we have 0, -17, and 17. So we're one step closer to that row echelon form. The last thing we need to do is get a 1 for that diagonal term. So the way you get zeros is by multiplying and adding so that you have opposite coefficients. The way you get ones is by multiplying, because essentially what I'm saying here, just so you're aware, is negative 17y equals 17. How would I solve for y? Well, I divide by negative 17. So it's essentially what we're doing here. We often write it in terms of multiplying. And so instead of adding and subtracting and multiplying and dividing, we can add either positive or negative, and we can multiply by a number or by a reciprocal. So you could either divide by negative 17 or just the reciprocal of negative 1 over 17 to each of those terms. So that's the more common method, so that you can say negative 1 over 17 R2 goes to R2. So you can multiply rows by anything and add them to another row. You can multiply a row by anything. You can even flop rows. I could have written this system the other way and it would still intersect in the same spot if I were to graph it. So my resulting matrix would be 0 times anything is 0, and then negatives cancel, and we have 1. That was the whole point. And then we have a negative times positive, that's negative, and 17 times the 1/17 is negative 1. So we have successfully converted this into row echelon form. 1's along the diagonal, 0 below. And what this tells us is that our y, remember this is 0x plus 1y equals negative 1 if I wrote it as an equation. So that simplifies just y is negative 1. So this just tells us y is negative 1. Then we go up to the other equation where we have 1x plus 3y equals negative 1. I'm just going to write that as x plus 3. Now I'm doing my back substitution. The value of y was negative 1. Simplifying and solving for x, we get x equals 2. So the answer to this system of equations is the point 2 comma negative 1. So I'm going to go through another example that's a little bit more involved and discuss some options, and we'll work with some fractions. So example 2. 2x minus y equals 9, and 3x plus 4y equals negative 14. So here's my system. I'm going to write it as a matrix. And it would be lovely if one of my equations had a 1x, and if it's on the top, it's ready to go. And if it's the bottom one, I just flip it to the top one. That's really nice. Imagine if this had been underneath, I would have written the original thing where these two lines would have been swapped, and then I would swap them so that the 1 is there. This case, we're not able to just swap rows and get a 1. So we could either divide the entire expression by 2, and I'd get fractions, or divide this entire equation by 3, but I'd also have fractions. So on this one, I unfortunately cannot avoid working with some fractions, which is why I'm actually doing this problem. However, I do want to mention that sometimes you are given expressions where you might have something like 2x plus 4y equals 10, and you could rewrite that as x plus 2y equals 5, just dividing both sides by 2, and you'd get your 1. So sometimes you luck out where you won't end up with fractions even if you have to divide. Okay, so in this example, we're trying to get it into row echelon form. So 1's on the diagonal, 0 below, and any number you want for up here. And so let's see, let's go ahead and divide by 2 or multiply by 1/2. So if I take half, and again, you can either use the notation to show it or show it like that. What you've done is you've done 1/2 of row 1 is now your row 1. So an equivalent equation, but with the 1 so that it's meeting this format. Now we need to get a 0 here. So we can multiply this top line by -3 and add it to this one. So sometimes people are able to do this in their head and just go -3 times 1 is -3 plus 3, that's 0. But especially when you have fractions, I like to do scratch work. So what I'm recording is my original matrix, my matrix as we move closer to that format. So when we have a 1, and then I'm recording with when we have the 0 also, and then I'll record when we have the 1, the 0, and the 1. So multiplying each of these by -3, and then adding it, and it might be helpful to write as you're doing this, write it with a common denominator so that we can add our fractions. So 2 times 4 is 8. Again, 8/2 is 4. And then for 14, 2 times -14 is -28. So when you divide, you would get back to -14. So when we add these together, we get 0, which was our whole goal. Then when we add these two fractions together, we get 11/2. And when we add these together, we get 55/2, -55/2. All right, so this is where that idea of multiplying by a reciprocal to get 1 is really going to come in handy. And it's also a good reminder at this point to think about the fact that the order matters. Had I not gotten that to be a 0 and I multiply by the reciprocal, then I would have had 2 11ths times some number, and it would not get us to 0, and it will just kind of go around in circles. So please go in this order. It really does simplify and prevent going around in circles more than necessary. Okay, so what we get from there is 0 times anything is 0. The 11s and the 2's cross cancel. We get 1. And then the 2's cross cancel, and the -55 divided by 11 is -5. So I'm recording this where I have it now in row echelon form. So the solution would be y equals -5, and then x minus 1/2, y equals 9/2. And again, if you're comfortable, you can go ahead and plug in your y as you're writing it. The other thing I'm going to mention is that you don't really have to be stuck with this. This was nice for the 1, and often it's nice if you're trying to solve for x that you have 1x. But in this case, because of fractions, you may find it easier to go back up to one of your original equations and plug it in so that you're dealing with integers. All right, so in any case, here we would have x plus 5/2 equals 9/2. Subtracting 5/2, we would have x equals 4/2, which is 2. So our answer is 2 comma, -5, x then y. If I had gone up and plugged it in where I was dealing with integers, it might be a little bit easier to work with since I don't have to work with fractions, but you get the same answer because these are all equivalent expressions. All right, I hope that helps with Gaussian elimination.